leads to. Okay? So before I start the talk, I would just also like to pay a very quick tribute. It's largely work in collaboration with Professor Padmanabhan, passed away last year. It's almost an year since he passed away, and I just wanted to highlight that there is a topical collection that we have with some very interesting articles as a tribute to Pat. So let me begin. What I'll do is I'll just start with an introduction to how I propose to go and study aspects of what I call as the zero-point length of space-time, essentially the structure of space-time at very small scales. Okay? And we will try to use a specific object, the Synge's world function, and I'll try to basically advertise why this is a better object than the standard metric tensor to describe the geometry of space-time at all scales. Not just at small scales, but specifically at small scales. It will give some new insights into the emergent gravity paradigm that I'll come to towards the end of the talk. Okay? I'll then describe some of the results that we have coming out of this formalism, and finally provide a broader outlook as to why bitensors provide a more natural set of mathematical tools to study space-time rather than local tensorial objects like the metric tensor that we are more used to. So let me begin. To begin with, let me just put the whole domain of research in the proper perspective. I like this figure from an old paper by Prakash. It's just a dimensional pyramid. So we usually would be working in the domain of quantum field theory in curved space-time. Okay, so it's not full-fledged quantum gravity. But what we are trying to do is see what insights it can give into the eventual some of the eventual broader features of quantum gravity. So that's the plane we are going to live in. And the key themes would be, as I already said, structure of space-time at small scales. But we would try to connect it up with some of the results we already know. I will very briefly mention these results because they are not a key focus of the talk. And the results are whether one can derive Einstein equations from thermodynamic arguments, starting with Jacobson, Paddy, and more recently the work on entropic gravity paradigm by Verlaine and all. I won't be talking about this, but try to make a connection as we go along. And also the nature of entropy itself in curved spacetimes, specifically the corrections, the curvature corrections to entropy of thermal systems. So these are to start with, these are the two key insights I would say that we have gained from semi-classical gravity over the last several decades. One is space-time can have thermal properties. An accelerated observer even in Minkowski space-time would see the inertial vacuum as a thermal bath. Right towards the end of the talk, I would try to present a result which corrects. This is essentially Unruh effect I am talking about, but I will try to present a result which provides at least partially non-perturbative corrections to Unruh temperature in curved space-time. Something that has not been looked at yet. Try to say something about its implications. But largely I will focus on the second insight from semi-classical gravity, which is that there most probably is an operational lower bound on our measurement of space-time intervals, which is provided by the Planck scale. Okay, and that's the feature we really want to capture. So since I am not going to be talking about the thermodynamic aspects of gravity for a while, let me quickly mention what I mean. So these arguments which try to derive Einstein equations from a thermodynamic starting point, they go something like this, that if you have a local acceleration horizon, so there's an accelerated observer in flat space-time, he or she will see a local acceleration horizon, and if you throw a mass or a hot cup of coffee across the horizon, you will lose some entropy. Those are the kind of starting arguments. You can actually then relate the product of Unruh temperature times the change of area of the horizon to the time component of Einstein tensor by using some purely differential geometric arguments. Okay, the sectional curvature of the acceleration horizon, they add up just in the right way so that basically the first law of thermodynamics looks very much like the Einstein equations GAV equal to TM. So, and this, as I already mentioned, has been looked at in quite some detail over the last several decades. What I am going to do is actually try to relook the structure of space-time at very small scales and see whether that has some hints about where these thermal properties of horizons are coming from. So that's the reason I mentioned it right at the beginning of the talk. It's based on these set of papers. So let me just go ahead. So the main question I would try to focus for the last part of the talk is whether metric tensor is the right candidate for describing the effective degrees of freedom that can lead to the kind of emergent gravity effects that I described just now. That is the first law of thermodynamics looking like or yielding Einstein equations, even higher curvature equations of state. So about the starting point itself, like I said, the key hint would come from the existence of a lower bound on operational measurement of space-time intervals provided by the Planck length, and there has been a history of work on this topic. Okay, I won't go through them, but essentially the existence of zero-point length is something that we all believe in. There would be such a lower bound, regardless of whatever framework of quantum gravity one eventually finds as the correct one. And there are some very basic arguments. You can use operational probes. You can use, for example, clocks and rods in space-time and actually get this bound very easily. Okay? So the paper I'm displaying here is a 1957 paper. It's a very famous model of clock, the Saliker-Wigner model. And you can construct a higher and higher generalized version of these points. So I think I've convinced you enough that there would be such an operational lower bound. And almost all these results, some of which are listed here, actually hint at the fact that if you modify the geodesic intervals between space-time events in some effective manner. One example is given here from a work by Bry-David, very old work by Bry-David, but it's not important how the distances are modified. What is relevant is that these are modified such that when the points are coincident, the distances don't go to zero, but they go to some finite value, which normally one would like to set as the Planck scale. Okay. So that is what I would take as a statement of the existence of zero-point length in space-time. So let me start by describing my basic variables. The variable I will focus on, as I mentioned in the beginning, is Synge's world function, which is simply 1/2 the square of geodesic distance between 2 points. So that's how it is defined. But it's a function which has to be given as a function of coordinates of both the points. Okay. That is what makes it difficult to compute in a generic space-time. Okay. And like I already mentioned, quantum gravity effects will be captured by demanding that the points are coincident. This distance function does not go to zero, which is not what one would normally expect from normal properties of a metric space. But then we are trying to incorporate some effective quantum gravitational correction, so we should not expect.
Could I interrupt you? So
sure.
you demand the minimal length?
Yes, yeah. And this is my statement for the demand.
And is that the observer independent or?
Yes, it will be observer independent. Yeah. Okay. So let me go further.
Thank you.
So,
no, thank you.
Sure.
Thank you.
Yeah. So let me just describe briefly some quick properties of this Synge's world function. So given any 2 points in space-time, you basically construct this object, which as I just said is 1/2 the square of geodesic interval between these 2 points. The gradient of this function at the 2 points will give you the tangent vectors at those 2 points. And if one looks at the textbook, it's a very good textbook on general relativity by J.L. Synge. He will describe a lot of interesting external properties of this world function and argue for the case as to why this is a better object to describe observable effects in curved space-time, contrary to what one usually finds in standard textbooks of GR. For example, things like redshift and all, things like redshift and everything can be neatly described in terms of world function. I will not have time to describe all these basic things, but the idea which I am trying to drive is that one can rewrite most of the results in standard GR in terms of world function or its concomitants, things derived from the world. Okay. So that's the first object that I am going to focus on. The second key object in the formalism would be what is called as the Van Dyck determinant. That is the object which measures the spray of geodesics from a given point in a manifold, any manifold. It doesn't have to be a Lorentzian spacetime, it can be a Euclidean manifold. So you take a point, you send out geodesics from this point. The density of geodesics is essentially what is measured by the object called as Van Dyck determinant, and that's going to play the second key role in the formalism. So with these 2 objects, what we are going to do is propose a replacement of conventional description of curved spacetime in terms of a metric tensor, with a description in terms of a distance function of 2 points, and see whether it can lead to any new insights. There is hope that this will be so because one can actually take derivatives of Synge's world function, take the coincidence limits, and show that you can have you can recover good enough of information about the metric, Riemann tensor, and higher derivatives of Riemann tensor from these derivatives and their coincidence limits. Okay. So it does capture a good deal of information that we already put in the standard metric formulation of GR, but in terms of this two-point object. So that's the pictorial depiction. What we expect is that at very large scales, you would recover a description of geometry where you can write down the metric as eta AB plus the curvature corrections, the standard Riemann normal coordinates expansion. But as you go to smaller scales, because you are demanding that there is a 0-point length in space-time, there would be some modifications and you will not get a standard metric structure. Okay? You won't even get a standard local metric tensor describing the structure of space-time at very small scales. Okay? So here are the two conditions from which I am going to build up and derive the final effective metric, so to say. Okay? What we will call as the Q metric. First condition I have already mentioned. What we are going to propose is that the geodesic distances are modified such that there is a 0-point length. This function S is arbitrary here. We need a full framework of quantum gravity to actually tell what that function is, how the distances will be modified. But we are not going to need it because all our final results will be in terms of S. Okay? We won't need the precise details of it, which anyway has to be supplied by a complete framework of quantum gravity. We are only going to demand that at the coincidence limit, this function reduces to Planck length. Okay? That's my statement for existence of a 0-point length. And the next condition is that a 2-point function, the leading divergent structure of the 2-point function, gets regularized because of the presence of this 0-point length. That's the work extracted from the work dating back to Bride, Evett and other people who showed that if you incorporate gravity in the picture, it will act as a universal regulator and the 2-point functions will get regularized at very small scales. So that's the second condition. Mathematically implementing this condition would naturally bring in the objects I introduced at the beginning of my talk, Van Dyck determinant and the world function, because the leading Hadamard form of the 2-point function actually depends on both those objects. So that's why those are the key objects that will enter the formalism. And then if you actually just look at the structure of the D'Alembertian operator acting on the 2-point function, you see that it can be written in terms of the extrinsic curvature of the surfaces generated by the geodesic space, whose picture I had just shown a while back. You take a point in the manifold, send out geodesics from that point, you go a constant geodesic length along all those geodesics, you get a surface. I call it as an equigeodesic surface. Its extrinsic curvature enters the expression for the D'Alembertian operator. Okay. So what we expect is that any condition we impose on the 2-point function will be captured by the world function and its derivatives. So that's the maths. I will not describe it, but just highlight that these are essentially the differential geometric identities related to the Van Dyck determinant that can help you impose the conditions on the 2-point function, which is going to be the key result that I am going to be after. So you use these identities, plug it here, and then impose the condition that the 2-point functions will get regularized at very small scales. So that's the picture I want to leave you with while describing the formalism. So essentially what we have done so far is taken an arbitrary space-time, just use the geodesic structure of that space-time, extracted objects like the world function and the Van Dyck determinant, and trying to impose the condition of existence of a 0-point length in terms of these objects. We are slowly trying to get rid of the metric tensor in the description of geometry of space-time by using these objects explicitly. So I think I'll just skip past these expressions. There are some very standard, although not very well known differential geometric identities connected with the geometry of these equigeodesic surfaces and the world function, which one can use to set up the formalism. There are covariant Taylor series expansions, which one can write for the Ricci scalar of these surfaces. In flat Minkowski spacetime, the surface which I have called as equigeodesic surface would just be the hyperboloids. You go constant geodesic distance from a point in Minkowski spacetime, you will get hyperboloids, and then it will just be the constant Ricci scalar of a hyperbolic three-dimensional space. And then there are further corrections coming when the space is not Minkowski. So after you do all this, the final result turns out to be that if you impose those conditions, if you impose the defined equations of the world function and the properties of the Van Dyck determinant, you end up deriving an effective metric which essentially looks like this. it has a conformal part, a part conformal to the actual metric tensor GAP, and then there is a part which depends on the tangent vector joining the 2 points. Okay, so basically this now is a formalism which is centered or anchored at a point P0 in the manifold, and this object is a bitensor which has 2 indices anchored at a point, the tensor indices anchored at a point P. So it's a second rank tensor at point P, but a scalar at point P0. So it's a bitensor in that sense. And it's what I call as dispermally related to the metric tensor GAP. If the second piece was not there, that would be just a conformal relation. This is a dispermal relation. And the most important part is that when the 2 points are coincident, this object itself is singular. However, it's not this object that we are interested in. We are interested in the curvature concomitants derived or built out of this object. So that's what I'm going to look at next. Okay. This is an object I'll call as the Q metric. That's going to be my effective metric. And let me just go further. This is some details about how that object is arrived at. I can go and go back to it if there are any questions. But what we are going to look at is what happens to the Ricci scalar built out of this effective Q metric. What you do is take that tensorial object that I just described and construct the Riemann tensor and the Ricci scalar from that object with P as the variable point, and then try to see how its various limits look like. Okay? And more interesting for us would be to take the coincidence limit of that Ricci scalar or Riemann tensor, which is more complicated, but it can be done, and then see whether in the L0 going to 0 limit one recovers the Ricci scalar of the background spacetime, the spacetime described by the metric tensor GAP itself. Interestingly, that does not turn out to be the case. So if you take the limits, let me just summarize the results in the table. So what happens is that if you take the coincidence limit of the biscalar, which I call as the Ricci scalar for the effective Q metric, and then set L0 equal to 0, the leading term that you get, which I am calling as SG for a reason here, will become clear in a moment, it's not equal to the Ricci scalar of the background metric GAP. So you have set Planck length to 0 at the end of this computation. You are expecting to get the Ricci scalar of the background geometry GAP, but that's not what happens. Essentially, the limits sigma going to 0 and L0 going to 0 do not commute, and that's why we get this particular result. So let me not go through the expression for the Ricci scalar, but just highlight what that SG was. The term which is the residual term that is left out, which we call it as the grain of the Cheshire cat, because once you set L0 equal to 0, you don't get back the Ricci scalar which you should have expected arising out of the background metric GAP, but you get something which looks like RAB, TATB. So there is some relic left of the fact that you had introduced the 0 point length in space-time in a singular manner, and that relic is visible in the curvature concomitants that you obtain from the effective Q metric. And it is this object which has been used, and that's the connection with the emergent gravity paradigm. This object has been used as the starting point of what is called as the entropy functional formalism that gives a different perspective on how to look at gravity, so that the equations, the Einstein equations or higher curvature gravitational field equations, look like the equations of thermodynamics. Okay. That was my initial part of the talk.
Sorry, Mac. Which way you compute those tensors? You simply substitute metric with metric, and it's the same structure?
Yes.
And is gamma.
Yes. And the reason for that is because the Q metric is a standard second rank tensor at the point P, but it's a scalar at the point P0. Okay. So you anchor your whole formalism in a geodesically convex neighborhood anchored at point P0 of the manifold.
So parallel transport, everything goes through the same?
Yes. Yeah. We don't quite know yet what to do with P0. Okay, because you can set up this formalism at any point of the given manifold. P0 will be sitting there as a parameter.
Sorry, what was sigma?
Sigma is sigma is the word function. I think it's from this slide or previous slide.
The two non-commuting limits. Sigma tends to 0 and L.
Yes. So sigma was the geodesic distance between the points P and P0.
Okay.
So basically, whether you bring the points together first and then set L0 equal to 0 is different from whether you set L0 equal to 0 first and then bring back the points. I'm trying to emphasize that the two limits are different and the difference is quite subtle. So I think I'm almost out of time, but I just wanted to highlight that such kind of relics coming out of using singular quantities and then taking parameter going to 0 has been known in other contexts. And this is one context in which it just happens to be relevant for the emergent gravity paradigm as well. So I will very quickly describe, I think I have 5 minutes left. I'll very quickly describe some of the results coming out of this. So the very quick and very interesting, neat and simple result to come out of this is to measure the volumes and surface areas of equigeodesic surfaces using the effective metric. If I am constructing an equigeodesic surface in Euclidean space, I would just get a sphere. We know what the area, surface area and the volume of the sphere is. If I instead use the Q metric for the same computation, I mentioned the sphere just to set the intuition right. It's a very, very simple calculation. But if you do the same thing using the effective metric, what you find is that although in the limit, in the coincidence limit, sigma going to 0, volume goes to 0 while area remains finite. That is just because of the singular structure of the Q metric. If I took a normal sphere in a Euclidean space, my area would go as r square, my volume will go as r cube. Both will vanish as r goes to 0. That doesn't seem to happen if you are using the effective metric. Okay? Essentially because the object itself is singular, and that singular nature is responsible for this non-trivial limit for basic geometrical quantities like volumes and areas. You can also compute the effective dimension, just like you would have done in standard Riemannian geometry. And it turns out that the dimension in the coincidence limit seems to fall from 4 at very large scales to 2 at very small scales. That's also quite a generic result regardless of the function s of sigma square, which I was expecting quantum gravity would provide me. You don't need that function. At least the limits are quite robust. Okay, how the curve behaves depends on specific choice. That's the one I've targeted for. Okay, so I'm just going to find it. So you can use this formalism to describe space-time singularities, which I will not discuss. I'll just mention it. The causal structure of light cones also get deformed if one is using the effective Q metric to describe the light cone. Light cones shrink in the coincidence limit. That can be useful for some of the quantum gravity formalisms. And finally, you can also say something about space-time becoming Euclidean at very small scales. Again, no time to discuss that, but if there are questions, I can go back to. And finally, before I end very quickly, where does it fit in the whole emergent gravity paradigm? And this, as I said, has essentially to do with the fact that you have reproduced as an effective action a quantity which very naturally appears in the emergent gravity paradigm, the entropy functional, which, when you vary in a specific way, can give you the connection between the laws of thermodynamics and the Einstein equations or its higher curvature generalizations. So that's essentially summarizing what I just mentioned. Also some implications for the entropy associated with the horizons. The regulator here is supposed to come from a 0-point length, and the effect, the Q metric can naturally provide an explanation of where this regulator comes from. So this is going to be my last slide. I will leave it there. Some of the results which I mentioned in the beginning but didn't talk about is that there is a non-perturbative correction to Unruh effect, and since Unruh effect lies at the heart of most of the arguments in emergent gravity paradigm, because you go to local acceleration horizons, use the Unruh temperature, and then say that TdS equals to dE equation is similar to the equation Einstein equations. The Unruh temperature, what is not very well recognized, is that gets corrected in curved spacetime even locally. I am not talking about effects coming due to finite size of the detectors, accelerated detectors, but just an effect coming because there is a Riemann tensor present. So this has implications for the equivalence principle, which can actually alter some of the connections we usually expect in emergent gravity paradigm. It can also affect the commutators, X and P commutators. If the dispersion relation P square equal to minus M square gets modified. And those are the broad message from the talk. That's my last slide. I just stop this.
Thank you. So we have time for some questions. Please.
Yeah.
Sorry, just a quick question. In one slide, you said that this formulation with the Synge's word function has almost all the things that all the information from the metric tensor.
Yeah.
What is not there?
Actually, it does carry all the information, but if you are just looking at 2 points and the Synge word function connecting the 2 points, then you for example would get Riemann tensor with symmetrized indices. Okay. The other components, to obtain those, you'll have to look at 3 points, 4 points, more points of the manifold. So I think the basic one is what is usually called as a 5-point detector. So you put 5 detectors cleverly located, look at the Synge word function between those points, and you can extract all the information about the background geometry from the structure of the...
Thanks.
Yeah.
Just very basic question. If the Synge word function has a minimum away from 0, so then just what happens when you cross the light cone? It's supposed to go to 0, right? So
Yes, that's actually a very good question. So you can use all of this as long as your sigma square is positive or negative, so space-like or time-like. For light cone, I have not described it, but there is you have to do the whole construction separately. Interestingly, most of the identities go through. However, the gradient of the word function for 2 points which are null connected has to be represented in terms of 2 auxiliary null vectors. So it has to be done more carefully, but a similar structure for the Q metric can still be written down. In fact, the Rai-Chaudhuri calculation, which I skipped, just displayed on the slide, makes use of the Q effective metric for null separated points.
Okay. Professor. Hello? Yeah. I just want to make a comment at 2 levels. At the conceptual level, you might find some moral support in the introduction I wrote in the paper in the year 2000. Basically saying that the 2-point function is probably more fundamental. And in fact, you can imagine that as kind of a simplified way to look at open strings. That was the hope at that point here. I'll give you the reference later.
Sure.
And technically, if you continue on pushing this line, you'll be working with a stress energy bitensor, right? And that
we actually have the stress energy bitensor. It is just a slightly incomplete piece of work.
Yeah.
But yes.
So you can actually, that leads to stochastic gravity, which has been developed for a long time. So
yes. No, I'm aware of this. I think I'll speak to you.
So you can make some use of that, that's what I'm saying.
Thanks.
Please, yeah.
Just a very fast question. Are the causal relations that we know affected by this approach, or do they still apply?
Sorry, what?
Are the causal relations that we know affected by this approach,
Yes,
or do they
yes,
still
yes,
apply?
yes,
Because
yes.
I think you have to rewrite and redefine things.
So for giving a complete answer to that, I would have to actually also go back to Aaron's earlier question. All I can say for now is that the structure of light cones get distorted in the manner I have shown here. This is purely coming out of the dispermal nature of the effective metric. Okay? So at very small scales, the light cones shrink, resembling something like asymptotic silence, but we have not explored this aspect too much. There are some conceptual issues which we need to clear. About the causal relation between events, we really need to look at the structure of the effective metric when the points are null separated. We do have that. That object looks slightly different from the one I have shown here, which is only for space-like and time-like intervals. So we have not yet explored the effective metric for null separated events sufficiently enough to say what happens to the causal. You are meaning causal ordering of events, right? Yes. So that we have not. We have the object for null separated point, but we have not explored it from.
And more than this, like low hyperbolicity and transitivity. And
Yes. That still remains. Yes. Yeah. But that has not been done yet. Yeah.
Okay, thank you very much. We have to stop.